Thank you for tuning in to This Automation Life, brought to you by Brenner-Fiedler. I'm your host, Jeremy Schubert. Each week, we discuss technologies used in automation. This week, Paul Oppenheim, automation specialist with Brenner-Fiedler, is here to discuss distance-based photoelectric sensors.
That was a mouthful, huh?
It was quite a mouthful.
All right.
Thanks for joining us today, Paul.
It's good to be here again, Jeremy. Thank you.
So, when we're talking about distance-based photoelectric sensors, quite a title, how is that different from a regular photo eye or a regular photoelectric sensor? What do you use it for that you wouldn't use a photo eye?
Excellent. Okay, so when you're working with what are called distance-based, you're thinking down the terms of measuring distance, usually toward and away from the sensor itself.
Okay.
So when you work normally with photoelectric sensors, for most general purposes where you're just looking for presence-absence, you have, as we kind of discussed in one of our previous podcasts, a photoelectric sensor that the transmitter is just a light-emitting diode or a laser diode, and then your receiver is just simply a photodiode. And it's just looking for light that's reflecting off of the target. If I see my own light reflecting back to the photodiode, my target must be present, send an output, and that's it. When you get now into distance-based, although the transmitter will still remain usually a laser-style transmitter, the receiver now has to be something that will now process the amount of light coming back with an analog-type format, as we kind of discussed with measuring devices in previous podcasts as well. So now you're looking at something where I have a target, and I want to know how far away I am from the sensor.
Okay.
Now we're bringing into where we work with a distance-based type sensor.
Okay. So is this different from, I've seen photoelectric sensors out there with a background suppression. Is that distance-based, or is that not, or is that kind of one of the an in-between gray area, or what?
Yeah, when you say something that has background suppression, that still kind of leads towards the original presence-absence type sensor, in which you're just simply using what we kind of call fixed field or fixed distance, saying I only see so far away. Anything beyond that, I'm blind to. And by I'm saying if I'm the sensor itself.
Okay.
I sometimes refer to fixed distance or background suppression sensors, the sensor that can't see beyond the end of its nose with a purpose. In other words, it's like it only can see so far. Anything beyond that, it ignores. And so that'll be in situations where you have like shiny backgrounds or something like that, and you don't want to see, let's say, something more than 3 inches away from you. But I do want to see something between, let's say, 1 to 3 inches away from you, regardless of its color, or luster, or whatever the case is.
Okay.
Now, when we kind of get now into more distance-based, now I want to know how far away I am. Am I 1 inch away, 2 inches, 3 inches, whatever the case is? Now we replace, like I said, the transmitter will still be, let's say, a laser, but now the receiver, instead of just a typical photodiode, now we'll have probably one of 3 type of light-gathering elements. And that's what we're going to talk about right now. And so,
so what are those?
That's good. There we go. Boy, like how I led that in there? Okay, great. So the most common type that's used, the most cost-effective out there, are known as PSDs. Well, those are called position sensing detectors, or position sensing devices. And what they do is just measure the amount of analog, or the amount of light that comes back. And it will, based on the amount of intensity that comes back, it can then judge how far or close the target is away from the sensor itself.
Okay.
And I'll get into some of the advantages and disadvantages of each. The next one that we normally would step up to would be either called like a CMOS or charge coupled device style. And what these are typically is you have an array of these receiving pixels, and as the light strikes each one of those, it will then kind of give you an idea of where your target is based on which pixel it hits.
Okay, so you know which pixel, and I'm kind of picturing the way you describe this as a line of pixels.
Right.
And when the light comes back, you can say, okay, this pixel in this linear position has the highest amount of light, so that's where my peak of light is coming back at.
That's basically it, right?
Okay.
Now, the position sensor device or detector, you're sort of kind of at the mercy of the target itself. So if you need something that's very fast and very cost-effective, PSDs are great for that, so long as the target that you're looking at is always going to be pretty much the exact same color and luster target.
Okay.
Because the amount of light intensity that's come back is going to be affected by that. So let's say, for instance, if I had kind of like a cream-colored matte finished target I'm looking at.
Mm-hmm.
And let's say I'm 3 inches away. Okay, I'm going to shine so much light back. If I'm 5 inches away, it's going to probably have less light coming back because I'm further away.
Okay.
Now, if I had that exact same setup where maybe I have a cream color target at 3 inches away, and now I have a black matte finished target,
Okay.
also 3 inches away, it might get confused and think that the black matte finish is actually further away.
Okay.
So because less light is reflected back because black absorbs light. So in that case, you could possibly get yourself in trouble using a PSD in that regard.
Okay, so the PSD is basically the location of the light, but it's like an average intensity of
Right.
that location type of thing. So,
Exactly. It still kind of works on kind of what we would call triangulation, where light comes at a certain angle, comes back at an angle, and it hits the PSD. But because you just simply have just the one light gathering element, and you're kind of spreading and it's trying to averaging the light across it, if you have different colored or different shiny targets, that could confuse it. Hence,
Okay.
you might not get the results you're looking for.
So I'm also thinking of some targets, let's say like a glue bead or
Right.
something else that's kind of a colloidal type, something that would absorb the light and spread it out.
Yes.
Would reflect a large beam, which would, I imagine, mess up the reading. Is
Sure,
that-
absolutely,
Okay.
right. So again, you have to kind of be careful. So although PSDs are very cost effective and they're very fast, there's not much intelligence required behind this.
Okay.
They're fantastic to use if the targets that you're looking at are identical pretty much
Okay.
every single time.
Okay.
Then those are great for that.
But if you have a color change, a reflectivity change,
Right
then
now we
you're
have to
probably
kinda
going to have a measurement change, which isn't what you want. You
Exactly.
wanna know
Now we
that
got to
real-
step it up to another level, and this is where you'd use like the charge coupled device with CMOS style,
Okay.
where you'd have basically an array of these pixels, like as we kind of alluded to before. Now imagine having several of these. Let's just say, for the sake of argument, 50 of them that are in a row, and let's say our measuring range is, let's say, from 1 to 3 inches.
Yeah.
And that's all that the sensor is able to see.
Right.
And those 50 pixels that's inside, let's say, the central processing unit, that array would represent from 1 inches to 3 inches.
Okay. So
Right,
you've got
so-
a number of pixels and you've got a number of inches. And
You got it. So basically, if I'm looking at a target, regardless of its color or luster, whatever light comes back, and if it struck pixel number 25,
yeah.
you can probably guess it's probably about 2 inches away, because let's say pixel number 1 represents 1 inch, the
Yeah.
50th pixel represents 3 inches.
Okay.
And there you go. So that'll give you kind of an
I
idea
gotcha.
where it's hitting it. Yeah.
Okay, and I'm sure that there's plenty of algorithms that they've put into these type of devices to figure out how do we find the right peak and the actual peak versus
Absolutely.
other straight. Okay,
Right, exactly. A lot of the more advanced ones you'll see out there as well are even more sensitive now, that when the light comes back, if you even had a darker target, even though it's striking the correct pixel, again, you can't control the fact that a dark target absorbs more light than a lighter, brighter target.
Mm-hmm.
So what it can do is also, if it says, okay, I'm seeing light hitting, let's say, that number 25 pixel, but it's kind of faint, if you will.
Yeah.
It actually, like you said, has algorithms that can then control the laser, what they would call laser flash time control, or the duty cycle of that laser beam.
Mm-hmm.
So that they can increase the energy of it to compensate for that.
Okay.
So that also will fluctuate as well.
Okay,
Kind
I
of just
gotcha.
depends on how big your pocketbook is.
Right. Okay.
Right. Yeah.
And so I guess stepping back a little bit for people maybe new to this, a lot of these are based on a triangulation. So
Correct.
you would send out a laser light, it reflects off of a surface,
Yes.
and it comes back and hits this receiving element that's a set space and angle in relation to the laser light that's coming out.
Right, and generally whichever pixel it would strike, if we're talking about the CCD or the CMOS style, whichever one it strikes normally at a 90-degree angle, in other words, dead on,
Yeah.
That's the one that normally would resonate, so to speak, for lack of a better term, say, that's the one calling in saying, you've hit pixel number 15, or whatever the case is, so you're probably between 1 and 2 inches away, and would report that back to you.
Okay, I gotcha. And so is there other capabilities that you could do with the CMOS or the CCD? Are you able to see if there's a clear target? Does it work better versus another type? Could you see like a clear target with something behind it, whereas the PSD maybe you couldn't?
Yeah, normally when you have the CCD or the CMOS style, and with that capability, now that you're kind of spreading that light over a whole array of pixels, a lot of the programmers behind the CPU can use it to their advantage, because sometimes, like for instance, if you wanted to measure, let's say, the thickness of glass, okay, you'll hit the top surface and the bottom surface of that glass. You might get two peaks that will come back.
Okay.
And so if the programmer, let's say, was clever enough in how designing his algorithm, he can say, okay, now two peaks are being reported in on two individual pixels, let's say. So if something hits, let's say, again, pixel number 25 and pixel number 50 report back in, you could say, that piece of glass is 1 inch thick.
Very cool.
Right.
Gotcha. Well, great. I think that's a complicated topic. So I think that's a nice overview and a nice entry into that.
Cool.
Cool. Well, that's all the time we have for this week. Paul, thank you very much for joining us, and
Certainly.
Thanks to everybody for listening to Brenner-Fiedler's This Automation Life. If you have any questions about what you just heard, or if you have a topic you'd like to hear discussed, please email us at tech, that's TECH, at brfa.com, and be sure to continue tuning in each week. We've got some upcoming episodes about communication protocols. I think we're going to talk about some nitrogen used in automation and manufacturing, and some other pneumatic topics.